Hello and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 21. Today we're going to talk about what does it mean to add two continuous random variables. And we'll start with a really concrete motivating question. But to bullet point the important topics here, we first need to make sure that we understand this notion of the joint PDF, which is essentially the two or higher dimensional analog of an ordinary PDF. And then once we've got that, we can understand what this process of summing two random variables gives us, sometimes called convolution. So here we're going to be asking the question of how to sum two continuous random variables, x and y, to get a new random variable, which is x plus y. And I'll try to give you an example where this actually comes up quite naturally. The main upshot here is that you'll learn that the PDF for z, x plus y, is not equal to the sum of the PDFs, but is instead equal to something called the convolution of x and y. In order to access this, we're going to need to quickly review how do joint PDFs work. All right, so let's get to it. So just remember that, so I'll do a little recollection here. So recall, a PDF is defined as a function, which we usually assume it to be non-negative, such that if I want to know what the probability of x being between two values is, I can just integrate the PDF of x between those two values. Sort of analogously, the PDF for a pair of random variables is a function little x, little y, such that if I want to know the probability that, let's say, x comma y is inside of some region A, and I'm just going to go ahead and draw A. Like this. If I want to know the probability that my pair of random variables lies in this region A, what I need to do is compute the double integral over A of the joint PDF of x and y. So this right here is the joint PDF, or maybe we'll call it JDF for short. All right, so we can go over some examples where this joint PDF is a little more complicated looking, but let's start with a really simple question, and we'll kind of ease into this. All right, so let's start with a concrete question. So here's our motivating question. All right, so suppose I construct a rectangle randomly by choosing its width which I'll just go ahead and refer to as its base x uniformly at random from 0 to 4. And its height from y, which I'm going to assume is uniformly distributed between 0 and 2. So once I construct this rectangle, I'm going to be interested in the following questions. How is its perimeter distributed? What is the expected perimeter? That, of course, being one of the summary statistics of any random variables, its expectation. And then finally, I can ask, what about other summary statistics, such as the variance? So we're going to be interested in answering these three questions. Now, for any good problem, you always want to try to first draw a picture of what's going on. So the basic idea here is, again, got my random variable x, which is going to govern the width of my rectangle. And then I've got my random variable y, which is going to govern the height of my rectangle. And I'm setting some pretty firm limits on what is the range of parameters that this can be. So let's say that this is 4, and about halfway up, rotate it over. Let's call this 2. And so just to communicate the picture here, so these are the range of possible pairs of values, x for the width and y for the height. And what's happening here is I'm going to throw a dart. Maybe it lands there. That's going to be the base, and that's going to be the height of my rectangle. So that's my rectangle. I can just think of it there. So here, I'd take another random draw, land there. That's my height. That's my base. There. That's my height. That's my base. All right, so I'm throwing my dart uniformly at random at this area, and then I'm constructing a rectangle whose upper right-hand corner is that point I randomly select. How is the perimeter distributed? Well, first, let me label some things real quick. So this right here, sometimes called this is the support of f of x, y. And this is, again, my joint density function. Now, in this case, it ends up equaling the product of the density functions for x and y because they're independent. And maybe just to emphasize that up here, I'm just going to go ahead and say this is done independently. All right, so again, I'm assuming here that I'm choosing these two things separately. Now, first of all, what is the PDF for this? Well, even if you didn't recognize independence, assuming that it's sort of uniformly at random, that means I need every point to be sort of equally probable within the region. And that probability has to be chosen such that the total probability is 1. So it's sort of easy to see that because my height here is 2 and my width here is 4, that this has area 8. So then 1/8 is the correct probability. This is for x between 0 and 4, for y chosen between 0 and 2. It's going to be 0 otherwise. So this is our JDF. That's always going to be step one. Step one is going to be find the JDF. All right, cool. So once we've identified what the joint PDF is, or JDF, we now need to figure out what are the possible values for this parameter. So here I want to make an observation. So I want to observe so my perimeter is going to be 2 times the width times 2 times the height is the perimeter. So I'm going to go ahead and simplify this discussion a little bit and just focus on what's the underlying thing here, which is that all I'm looking at really is 2 times the sum of x and y. So let's let S equal x plus y is the sum. This is going to be my core object of study. All right, because we're talking about sums of random variables, but in this case, we can geometrically think of this sum as being half the perimeter. All right, so again, just to reiterate, what's going on here is, I'm randomly selecting a point, bing, that's going to be my particular instance of x and y, and now I'm interested in summing up the perimeter of this rectangle. And I'm circumventing that by instead considering how is the sum distributed. All right, so we've identified the JDF and we've broken down the problems now considering the sum of these things. Let's go ahead and try to figure out what are the possible sums associated to this joint probability density function. And so I'm just going to go ahead and redraw it. So key observation here is that if I want my sum to equal some fixed value, I can compute the probability density of that sum by considering the length of this slice through my PDF. And so this is going to be formalized in sort of step 2 here. So step 2 is for varying values of little s equals little x plus little y, where this line intersects the support of my JDF. And again, we think of the support here. This is the region of points. These are points where f of x, y, our little JDF is not equal to 0. because we know we don't need to integrate the 0 function. We just need to integrate whatever the where this is non-zero. So let's sketch a couple of possible values. And so remember, when you think about the equation of the line, you know, s equals x plus y, you could always rearrange this to think about, well, what this is really saying is that y is equal to s minus x. And so notice that has negative slope of 1, slope negative 1. But its offset, or its y-intercept, is determined by this sum value here. So what are our possible values of s? And then let's highlight places where there's some sort of dramatic change in the behavior. Well, here's a situation where s equals 0. Now, what are the limits of integration, at least viewed with respect to x, when I'm at this next slice here? So this slice right here. Notice that what happens is I go from x equals 0. And if I plug that in to my equation, you'll see that where this equals, where the y value equals 0 corresponds to when x is equal to s. And so there's another sort of change in behavior when this line passes through that corner, because notice that whereas here, the intercept with the support occurred on this y-axis, which is also where x equals 0. Over here, it only enters the support at a different value. It doesn't enter at the value of x. We need to figure out what is the equation of this point. All right, so we got what is the equation for this point? Well, let's think about it. So we know that s at this point is greater than 2, because here is where s equals 2. So now if I got some value s, and again, if I plug in y equals 0 here, then this requires that x equals s. What is the equation here? Well, this corresponds to where y is equal to 2. So y equals 2, and I plug that in to this equation right here. And then I can see that, I need x to equal s minus 2. So just double check that works real quick. So if I do s minus 2, then I do get y equals 2. All right, good. So we now have the limits for this point and this point. And again, this corresponds to x equals s. So it turns out that for all the values of s between this and this and this and this and this, I can always determine the x coordinate just by whatever the sum is, which makes total sense, because if I set y to equal 0, this is 0, then s equals x. So that makes good sense. Now, something again changes when I pass through this slice here. So now I'm looking at a point where x equals 4 is the limit. So that's the largest value that x can be. Which, again, if you plug in, means up here that, that y is equal to, again, 2. or correspondingly to s equals 6, because you sum these two together here along this line. Now what happens right when we're above this? So now we're in a region between s equals 6 and what's, sorry, my apologies. So if x equals 4, then in this case, sorry, no, this is still where x equals 4. S equals 4, my apologies. Yeah, because over here, then x equals 2 halfway through, and then y equals 2. So this is also where s equals 4. Yeah, the part I was confused by was that, of course, the largest value for the sum, when you have these two values here, y ranging between 0 and 2 and x ranging between 0 and 4, the biggest sum you can possibly get is 2 plus 4 is 6. All right, but now let's determine the limits of integration up here. I guess I didn't need to draw that because I could just compute it here. Well, here, obviously, x equals 4 is the largest value. Now, what is the value for s? Well, we get the same equation that we had actually before, which just comes from plugging in x equals 4 into, or sorry, y equals 2 into this expression. So if y equals 2, then x has to equal s minus 2. All right, very good. All right, so that seems pretty complicated, but let's go ahead and just work out the integral. And what we're doing here is we're determining fundamentally this sum, which is that the probability that x plus y equals s is governed by the integral, and we'll have some x limits that we've just discovered, but it's all we're doing here is looking at the places where x plus y equals x, which is the same thing as saying that x is x and y is equal to s minus x, right? Because this is y dx. And so the purpose of this exercise above was we just had to figure out what were our limits of integration as a function of s. All right, so let's go ahead and do it. So first, we're going to assume that s is between 0 and 2. This corresponds to where we are in this region of possible values for the sum. So what we already determined here is that I'm going to integrate from x equals 0 to x equals s. And I'm going to be plugging in this. I'm going to be looking at the length of this slice here. So what does that look like? So the probability that x plus y equals s is the integral from x equals 0 to x equals s minus 2, or x equals s of 1/8 dx. Well, that just ends up equaling s over 8. All right, so I've now determined my PDF for s for at least this range of values. So let's go ahead and do the next one. So for s between 2 and 4, well, things are a little different here. So I'm now past this value, and I'm now starting to look at these kinds of values where my x limit of integration corresponds to s minus 2, and my limit here corresponds to s. So just to review that here. So I'm trying to figure out the length of this line. So what I'm going to do is integrate from this point, which corresponds to s minus 2, all the way to s. And of course, s minus 2 is less than s. let's just do it. So s minus 2 to s 1/8 dx. Now the reason we're doing this is because you're going to see, again, this is a function of little s, because our PDF usually is a function of whatever little version of the variable we're looking at. So I have now 1/8 times s minus 2. And then this gives me a fourth. So that's kind of interesting. It just tells you that, and again, this makes perfect sense, is that this length here is the same for all these values in this range here. And that range is from s equals 2 to s equals 4. Yeah, again, see that? You see that the lengths are all the same? But not that one, because once we move up past that value, you have less and less length here. Just like before this value, we had less and less length. So kind of what we're seeing here is that the probability is going to ramp up, plateau, and then start to ramp back down. So let's go ahead and see that using calculus. All right, so I need to determine what's the lower limit of my integral. All right, well, s minus 2 still, but now my upper limit isn't some arbitrary value of s. It's equal to 4. This is because it tells me I'm running out of area here. So I'm going from s minus 2 to 4, again, of my uniform PDF, which is going to be 1/8 times 4 minus s minus 2. So that works out to what looks like, sorry, maybe I'm being a little too fast there. So 1/8 times 6 minus s. And maybe I'll just leave it like that, because the only simplification you can do is divide both by 8. All right, so now I'm in a position to graph what this PDF looks like. And again, just to step back and think about what's going on here. I'm trying to figure out what's the probability that x plus y equals a given value. Now, the probability that x plus y is equal to a given value is the same thing as the probability that y equals s minus x, which is, I take a line, whoops, I take a line that looks like y equals s minus x, and I figure out what's the intersection of that probability, of that line, with the probability of possible values for x and y. And so you can see here that the intersection is small. And then here it reaches a constant value, which is a fourth of the total probability. And then it starts to decrease again. So let's go ahead and draw that. So this, what we've been doing right now is effectively step 3, which is integrate. All right, so I'll go ahead and maybe list this as an unofficial step 4. Which is write and draw the PDF. All right, so what do we've got here? So now we're looking at the distribution of possible values for s, and I'm looking at the probability of that value. Here's a little s, and here I'm going to be interested in drawing the probability density. So we already agreed that there were these 3 main regions of behavior, from 0 to 2, from 2 to 4, and then from 4 to 6. And the way my PDF grows is first it's an eighth of whatever the sum value is. It plateaus at value a fourth. This is s divided by 8. And then it starts to go down using the same slope as it went up, but now negative. 6 minus s over 8. And if you plug in s equals 4, you get that 6 minus 4 over 8 is 2/8 is a fourth. So that this is in fact a continuous function. And that's an s here. This is also a fourth. And then it's 0 outside of here. So the PDF for s now looks like s over 8 for s between 0 and 2. It's 1/4 for s between 2 and 4. And then it's 6 minus s divided by 8 for s between 4 and 6. And it's 0 otherwise. So notice in no way was this equal to the sum of the two PDFs for x and y, but instead it came from sort of counting possibilities on these anti-diagonals. So I'm just going to go ahead and write that out in bold here. So note that the probability of a sum is not the sum of the probabilities. I'm just going to box that and put it in red because that's a mistake you don't want to make. And think about it, this kind of makes sense, right? Because when we considered in the discrete case, and we had x equals the value of rolling a die, 6-sided die, and y was equal to roll a 6-sided die again. And then if you considered their sum, you got an interesting distribution, which on the low end was 2 and on the high end was 12, but then it peaked as you went up to the most common value, which was actually 7. So again, even though these were uniform on 1 through 6, when you consider the possible sums, you have to consider the ways in which they add up. And this was exactly the analog of the process we did here. So we had 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And now you look at possible values for the sum. That effectively involved going across these diagonals, where we had 2 and 3 and 4 and 5 and 6 and 7, 7 having the longest intersection with this sort of rectangle of possibilities. In this case, it actually looks like a square. And so consequently, this was the most probable. Now, the difference here is because we have a larger range of values for x, we sort of reach a plateau. And so that plateau persists for a bit longer. All right, so we're almost done, but not quite. And let me just sort of summarize real quickly. So high level summary. So the above steps, which included 1, identify the JDF. For finding the PDF for S equals X plus Y was 1, identify the joint PDF for X and Y. 2, determine possible values for S. The limits of integration in terms of S3 integrate, and 4 write and draw. These are the steps for computing what's called the convolution. Convolution of X and Y, which we sometimes write as follows. So this way. So F of this is the integral over the set of points where X plus Y equals S of F of X, S minus X dx. Sorry, there's one too many limits here. And so is the PDF for S. And so again, here, this is the joint PDF. And this formula works sort of regardless of whether or not X and Y are independent. Although we sometimes only refer to convolution when we're looking at independent random variables. All right, so back to the question here. And so here we're going to get to display some of the other things we've been working on here. So remember the parameter, which we call P, is equal to 2 times the sum. And we know the PDF for S now. But how do we determine the PDF for P? Knowing that P is 2 times S. So here we need to apply the formula. Which says that if, Y is some function, let me just say it this way. So if Z is equal to some function AW plus B, then the PDF for Z is equal to 1 over the absolute value of A, the PDF for W evaluated for z minus b divided by a. So that's the PDF for W. And this is now going to be the PDF for Z. So in our case, we're not adding or subtracting anything. A equals 2. So now we know that the PDF for the perimeter is simply 1/2 f of the sum, but where I've also had to stretch out the values of that sum. So I take p divided by 2. So if I sketch this, and remember, this was the PDF for S, what ends up happening is that the PDF for P, which is 2 times S, well, now we have twice the possible value. So we go from 0 to 12, which is 2 times 6. And now instead of going up to a 4th, plateauing and then going down, we go up to an 8th. Oops. Now let me identify. So now we have to go from, so this is 4, and now this is 8. And now this is a value of an 8, which makes sense because this is 1/2 the PDF for S evaluated on 4 divided by 2, which is 2, which equals 1/2 times a 4th is an 8. So this ends up being our PDF for the perimeter. It ends up stretching out. Now, if we want to do things like compute the expectation and such, we're in luck because things like that are easier. So let's do expectation real quick. So we know that the expected perimeter is the same thing as E times the expectation of 2S, which is by linearity of expectation, 2 times the expected sum. But what is the expected sum? Well, we know that by definition, S is the sum of my 2 random variables, which again is by linearity of expectation, the sum of the expectations. So recall X was uniformly distributed from 0 to 4, and Y was uniformly distributed from 0 to 2. And so the general formula is that the expectation of something that is uniformly distributed from A to B is equal to B minus A divided by 2. So now when we apply that in this case, we now know that this is equal to 4 minus 0 divided by 2 plus 2 minus 0 divided by 2, which is going to be 2 plus 1 equals 3, which implies now that the expected parameter 6, which is kind of what you'd think. And notice again that this sort of ends up being the some of these sort of maximum values here. Which ends up being 2 times that. So one more thing. So what about variance? So this is a situation where we need to use the facts that X and Y were independent. So if X and Y are independent, then the variance of X plus Y is equal to the variance of X plus the variance of y. And so I'm going to also put to good use the variance formula for the uniform distribution, which ends up equaling b minus a squared raised to the divided by 12. So in our example here, we know that a is 0 in both cases. B is either 4, so that's going to be 16 over 12. Or we've got over here, this ends up being B is 2 and A is 0, so this ends up being 4 over 12. So this ends up equaling 20/12. For the sum, and now we can use the fact that variance of A times W is equal to A squared times the variance of W. And I'm just using W to denote any random variable. So that then allows me to say that the variance of 2 times S, which is our P, ends up being 4 times the variance of S, which is 4 times the variance of X plus Y, which is 4 times the variance of X plus the variance of Y. We just computed this over here. I think we said 20/12. So it's 4 times 20/12. So that 3 goes in the bottom. So we end up having 20/3. That ends up being the variance for the perimeter. So I know this feels like a lot, but it ends up actually being fairly simple once you get some practice to it, especially in the situations where X and Y are independent. Now let me make some quick comments on what happens when X and Y are not independent. Let me give you an example where this occurs. It's remarkably commonplace is if I throw a dart at a dartboard, here X and Y are not independent. And this is where I assume I hit uniformly at random the dartboard, the board. Now, why is this not independent? Well, if I think about what is the support of possible X values, it looks something like this. And if I look at the support of possible Y values, it looks like this. Now, if X and Y are independent, and this actually is an if and only if, then the joint PDF is equal to the product of the individual PDFs. But if I consider a point like this one right here, so again, f of X of this little X value is not equal to 0. And similarly, since it's a possible Y value, f of Y of little y is not equal to 0. This would be something that's not 0. So not 0. But I see it's off the dartboard. So then I would end up saying that 0 is not equal to not 0. And that's obviously a contradiction. So in this setting, we know that these things are not related. Now, again, the formula and process goes through exactly as intended. If I want to compute sums, I just need to find the limits of integration where this intersects. And so in that sense, everything goes through fine. But I do want to mention that we have this important special case, which is when I consider the sum of two random variables that are not related or are not independent, then the true value of the variance of the sum is the variance of x plus variance of y plus 2 times the covariance of x and y, where the covariance of x and y is equal to the expectation of x minus its mean times y minus its mean. And this is true always. It just so happens that when x and y are independent, then this covariance is equal to 0. And so this ends up being one of the building blocks as moving into statistics and finding relationships between random variables is by looking actually at their covariance. But I wanted to offer that to you now so that we could consider the situation where suppose we are working with two not independent random variables and we're interested in what is the variance of their sum. All right, so that's it for today. I look forward to seeing you in class soon.